We're going to begin to visualize our variables with graphs. While we start with graphing one variable at a time, we'll use this as a springboard for ultimately visualizing multiple variables simultaneously within our graphs. We're going to keep it simple. We'll use R code to generate graphs that help us learn more about our data and to make decisions about next steps in our research. We're focusing on the function of graphic visualizations rather than producing polished presentation-ready graphs. Bar charts are most commonly used to examine the distribution of individual variables. Here we show the distribution for the random sample of 1,200 U.S. college students who were asked, "What is your perception of your own body?" In this bar chart, the X, or horizontal axis, includes the three response categories: underweight, overweight, and about right. In the first bar chart, the height of the bars is measured on the Y, or vertical axis, as the number or count of college students giving each response. The second bar chart shows the same data, but as a percentage of the total sample. A bar chart helps us display the distribution of a categorical variable, for example, percentage of observations in each category. If you'll recall, the data managed variables of interest in our sample project are now tab 12 MDX, representing a diagnosis of nicotine dependence in the past 12 months, and numsigmo_EST, representing the average number of cigarettes smoked. Code we used previously to request the frequency distribution for each of these variables of interest. If we run our program, the output will of course include frequency distributions for these two variables. However, in addition to frequency distributions, we now want to examine the corresponding bar charts for these two variables. The bar chart is one of the most frequently used graphic visualizations. In R, we will use the ggplot2 package for graphing. You'll need to install the package by going to the Tools tab at the top, then selecting Install Packages, and then typing ggplot2 into the box. Finally, click Install. When R has finished installing the package, you need to load the package by typing library, parens, ggplot2, close parens. Here's the basic code for a univariate graph of a categorical variable. ggplot parens data equals data, close paren, plus geom_bar, parens AES, parens x equals categorical variable name, close parens, close parens. The first term, ggplot parens data equals data close parens, tells R that you're going to create a plot from the data set called data. This term cannot stand alone. Rather, R is expecting additional terms to come after this that specify what R calls the geometry of the plot. The geometry essentially means the type of plot that you want R to create. Here, we want a bar plot. So after the ggplot term, we need to add a plus sign, followed by the function geom_bar. Inside the geom_bar function, we need to specify what R calls the aesthetics, which means the variable that gets plotted and where on the plot it should appear. Here, we're specifying our selected categorical variable as going on the x-axis. First, before creating our bar plot, we need to make sure that the variable is stored as the correct type in R. We can check this using the str command, which means structure. If we enter and run str parens data tab 12 ndx close parens, the output says factor with two levels 0 and 1, which means tab 12 mdx is correctly stored as type factor since it's a categorical variable. If your output says something else, such as int for integer or num for numeric, that would mean we forgot an important data management step previously. In that case, we can quickly correct it by typing and running data tab 12 mdx assignment arrow as .factor parens, data $ tab 12 MDX, close parens. That's using the as.factor function. Once you've double-checked that your categorical variable is stored correctly as type factor, you're ready to start creating your bar plot. When graphing with the ggplot2 package, it often helps to create a small temporary data subset with certain features to enable easier graphing. First, we need to create a subset for plotting that contains only the unique ID and the variable or variables that will be plotted, and removes all NAs in those variables. We'll call this temporary data subset data.plot.tab12mdx, and we do this with the following command: data.plot.tab12mdx, assignment arrow, na.omit, parens, sub1, bracket, comma, c, parens, quotation marks, id num, close quotation, comma, quotation mark, tab12mdx, close quotation, in paren, close bracket, close parens. This command does both things. Creates a subset that only includes tab12mdx, the categorical variable that we want to plot, along with the unique identifier, and also removes all NAs in that variable so they don't appear in the bar plot. Second, since this is a categorical variable and we want descriptive labels to appear on the plot rather than dummy codes, we're actually going to do some data management to the temporary plotting data set so that we replace the dummy codes with descriptive labels. Levels, parens, data.plot.tab12mdx, $tab12mdx, close paren, assignment arrow, C, paren, quotation mark, no dependence, in quotation, comma, quotation mark, dependence, in quotation, close paren. Here, we're taking the existing levels, that is, the possible responses in this variable, which are 0 and 1, and setting them to the list of phrases no dependence and dependence. Please note that the order is very important here. The first phrase should correspond to the lowest value, 0 for no dependence, and the second phrase corresponds to the second value, 1 for dependence. Now that we have our separate small data set just for plotting, our basic bar plot command starts like this: ggplot parens data equal data.plot.tab12mdx, close paren, plus geom_bar, paren, AES, paren, x equal tab12mdx, close paren, close paren. However, in order to add labels for both the x and y axes, you need to add components to the ggplot2 function. You use a plus sign at the end of a ggplot command line to add a component. Note that your command can span multiple lines by pressing Enter after the plus sign. That is, as long as you end each intermediate line with a plus sign so that R knows to wait for the remaining commands before it plots anything. For every new component you want to add to the plot, you always add a plus sign to the end of the ggplot command line along with the function describing the new component. To add a label for the x-axis, go back to the end of the ggplot command and add on the line a plus sign followed by the function xlab. Inside the parentheses of the xlab function, you need to provide, in quotation marks, a descriptive label for the variable plotted on that axis. To add a label to the y-axis, the name of the function is ylab. So, ggplot parens data equal data.plot.tab12mdx, close paren, plus geom_bar, paren, AES, parens, x equals tab12mdx, close parens, plus xlab, parens, quotation mark, nicotine dependence in past 12 months, close quotation, in parens, plus ylab, parens, quotation mark, frequency, in quotation, close parens. Here's the code inserted in our sample program. And we just save and run the entire program to generate the requested bar chart. Here's the bar chart we asked R to generate. It shows the number of young adult smokers with nicotine dependence and those without nicotine dependence. Remember that num_EST is the estimate for the number of cigarettes smoked per month. Because num_EST is actually a quantitative variable, the syntax we use in the program is slightly different. To visualize a quantitative variable, we will use the ggplot function and the geom_histogram function to generate a histogram. In this case, we may use our main data set rather than creating a special one for graphing a histogram. ggplot paren data equals sub1 close paren plus geom_histogram paren AES parens x equals num_EST close parens. When you run this, you'll see that R generates a graphical distribution of a quantitative variable, that is, a histogram. In a histogram, intervals of values are plotted on the x-axis rather than discrete or separate values. From the bars here, you can see that what is displayed is the midpoint of the intervals. Note that after you run this command, R gives a message about the bin width, which appears in the console. Typically, we don't specify the width of the bars for a quantitative variable, as R will create a display that best represents the distribution. So we can safely ignore this message and go along with R's default bin width. The geom_histogram function takes the quantitative variable as input for the x-axis. We can also add other optional inputs like the named arguments, xlab and ylab, introduced earlier. The argument ggtitle specifies the main title of the histogram. Let's look at a more basic example of how a histogram might be constructed, and then use that as a springboard for talking about additional descriptive statistics that can be generated for quantitative variables. In this example, we have the exam grades of 15 students. We first need to break the range of values into intervals, also called bins, groups, or classes. In this case, since our data set consists of exam scores, it'll make sense to choose intervals that typically correspond to the range of letter grades. So 10 points wide, 40 to 50, 50 to 60, etc. By counting how many of the 15 observations fall in each of the intervals, we get this table. To construct the histogram from this table, the intervals are plotted on the x-axis and show the number of observations in each interval, or the percentage of observations in each interval, on the y-axis, which is represented by the height of the bar located above the interval.
Once the distribution has been displayed graphically as a histogram, we can describe the overall pattern of the distribution and mention any striking deviations from that pattern. More specifically, we should consider the following features. We will get a sense of the overall pattern of the data from the histogram's center, spread, and shape, while outliers will highlight deviations from that pattern.
When describing the shape of a distribution, we should consider symmetry or skewness of the distribution and peakness or modality, that is, the number of peaks or modes that the distribution has. Here, all three distributions would be referred to as symmetric, but they're different in their modality or peakedness. The first distribution is unimodal. It has one mode, roughly at 10, around which the observations are concentrated. The second distribution is bimodal. It has two modes, roughly at 10 and 20, around which the observations are concentrated. The third distribution is kind of flat or uniform. The distribution has no modes, or no value around which the observations are concentrated. Instead, the observations are roughly, uniformly distributed among the different values. A distribution is called skewed right if the right tail, the larger values, is much longer than the left tail, or smaller values. Note that in a skewed right distribution, as you can see here on the right, the bulk of the observations are small to medium, with a few observations that are much larger than the rest. An example of a real-life variable that has a skewed right distribution is salary. Most people earn in the low to medium range of salaries, with a few exceptions, such as CEOs, professional athletes, etc., that are distributed along a large range, that is, the long tail of higher values. A distribution is called skewed left if the left tail, or smaller values, is much longer than the right tail, or larger values. Note that in a skewed left distribution, the bulk of the observations are medium to large, with a few observations that are much smaller than the rest. An example of a real-life variable that has a skewed left distribution is age of death from natural causes. Most deaths from natural causes happen at older ages, with fewer cases happening at younger ages. Skewed distributions can also be bimodal. Here's an example. A medium-sized neighborhood 24-hour convenience store collected data from 537 customers on the amount of money they spent in a single visit to the store. The histogram displays the data. You can see that the amount of money spent is concentrated around $20 and then concentrated again around $50. From the Mars crater data set, we also display the latitude of the Mars crater's rims. The values are concentrated around 66 to 69 decimal degrees north, and again around 36 decimal degrees north. So the mode or modes of a variable are the values that occur most often, and knowing this can help you make better decisions. The mode, for example, has applications in book publishing. Not surprisingly, it's important for the publisher to print more of the most popular books, because printing different books in equal numbers would cause a shortage of some books and an oversupply of others. Likewise, the mode has applications in manufacturing. For example, it's also important to manufacture more of the most popular shoes and shoe sizes.
Now, as we've seen, the mode is not always at the center. The center of distribution is its midpoint, the value that divides the distributions so that approximately half the observations take smaller values and approximately half take larger values.
As you can see from the histogram, the center of the grades distribution is roughly 70. We can get only a rough estimate for the center of the distribution. 7 students scored below 70 and 8 students scored above 70. Estimates can often be made from examining a histogram. So what about spread? The spread of the distribution, also called variability, can be described by the approximate range covered by the data. From looking at the histogram, we can approximate the smallest observation, or minimum, and the largest observation, or maximum, and thus approximate the range. In our exam score example, you can see that the approximate minimum is 45, that is, the middle of the lowest interval of scores. The approximate maximum is 95, the middle of the highest interval of scores. So our approximate range is about 50 points, 95 minus 45. The overall pattern of the distribution of a quantitative variable is described by its shape, center, and spread. By inspecting the histogram, we can describe the shape of the distribution, but as we saw, we can only get a rough estimate of the center and spread.
In order to describe the distribution of a quantitative variable, you also need precise numerical descriptions of the center and spread.
The mode is a kind of average. There are 3 kinds of average, and each one tells us something different. so we need to make sure we understand what each average means.
When we use the term average, we mean one of three things usually. Either we mean the mean average, or we mean the modal average, or we mean the median average. It's very easy to understand the difference between these, especially if you've played darts before. I threw 2 lots of 3 darts, and in my 6 darts I scored a 2, 3 threes, a 12 and a 13. Now let's see if we can work out the mean, the median and the mode. First of all, the mean. We take the total of all the 6 scores and divide by the number of observations, and that's the mean. If we want the modal score, we simply look for the most common score, the most common number of observations. If we want the median score, we write the scores down in ascending order and then look for the middle value. Now there's a slight problem here that we have an even number of observations, so we take the 2 middle values and work out the mean average of those 2. So for my not very good dart playing, our scores were 2, 3, 3, 3, 12, 13. The mean is 2 plus 3 plus 3 plus 3 plus 12 plus 13 divided by 6. 36 over 6 equals 6. The mode is 3. The median, since we have an even number of observations, is 3 plus 3, the middle 2 observations, divided by 2, which equals 3. Notice if the dart player had scored, say, 19 instead of 13, the mean increases to 7, but the mode and the median score is unchanged.
So let's briefly review numerical measures of center. Intuitively speaking, the numerical measure of center is telling us what is a typical value of a variable's distribution. The 3 main numerical measures of the center of the distribution are the mode, the median, and the mean. So far, when we looked at the shape of the distribution, we identified the mode as the value where the distribution has a peak. And we saw examples when distributions have one mode, that is, a unimodal distribution, or 2 modes, a bimodal distribution. In other words, so far we identified the mode visually from the histogram. Looking at our histograms again, we can easily see the mode. It's the most common occurring value in the distribution. The median, that is, the midpoint of the distribution, is the number such that half of the observations fall above and half fall below. We find the median by ordering the data from the smallest to the largest. Consider when n, the number of observations, is even or odd. If n is odd, the median is the center observation in the ordered list. When the number of observations is even, the median is the mean or average of the value of the 2 center observations. The mean, of course, can be calculated by adding up the values for all the observations and dividing by the number of observations in order to generate a mean average. Our goal here is to describe the distribution. How would you describe these 2 distributions of exam scores? Both distributions are centered at 70. The mean of both distributions is approximately 70. But the distributions are really quite different. The first distribution has much larger variability in scores compared to the second one. In order to describe a distribution, we need to supplement the graphical display not only with a measure of center, but also with a measure of the variability or spread of the distribution.
There are several ways to describe spread. A commonly used measure is standard deviation. The idea behind the standard deviation is to quantify the spread of the distribution by measuring how far the observations are from their mean. The standard deviation gives the average or typical distance between a data point and the mean. In order to better understand standard deviation, it would be useful to see an example of how it's calculated. In practice, of course, the software will be doing these calculations for us.
Emergency medical services companies would like to estimate how many ambulance crews to keep on standby. Here are the number of ambulance calls over an 8-hour period. To find the standard deviation of the number of hourly calls, first we would find the mean of our data. Next, we would need to find the deviations from the mean, that is, the difference between each observation and the mean. Since our mean is 9, we would subtract 9 from each of our observations. As a third step, we would square each of these deviations. Next, we average the squared deviations by adding them up and then dividing them by n minus 1, that is, 1 less than the sample size. This average of the squared deviations is called the variance. The standard deviation of your variable is the square root of this variance. So why do we take the square root? Note that 16 is the average of the squared deviations and therefore has different units of measurements. In this case, 16 is measured in squared number of ambulance calls, which obviously cannot be interpreted. We therefore take the square root in order to compensate for the fact that we've squared all of our deviations, and also in order to go back to the original unit of measurement. Recall that the average number of emergency calls in an hour is 9. The interpretation of standard deviation equal to 4 is that, on average, the actual number of emergency calls each hour is 4 away from 9. Another way of saying this is that there's an average of 9 ambulance calls in each hour, plus or minus 4. Since we're working with very large numbers of observations, hand calculations of standard deviation really aren't feasible. R will do all these calculations for you, but it's important to know how to calculate standard deviation so that you can make sense of variability. For example, looking at a variable's distribution in 2 different samples, you should be able to tell which has greater variability, that is, a larger standard deviation. To request general summary statistics for a quantitative variable, you can use the summary function. A template for this function looks like this: summary, parens, data, $, quantitative variable name, close parens. This function reports the minimum, mean, and maximum values, among other things. In addition, R has the SD function to calculate the standard deviation of a quantitative variable. SD parens data $, quantitative variable name, comma, na.rm equal true, close paren. R will return NA if you directly try to calculate the standard deviation of a variable containing missing data. For example, if we use this code to calculate the standard deviation of the variable numsigmo_est, which does contain missing data, you can see the R return of NA. To generate the standard deviation based on valid data, we need to include na.rm equal true, which will remove any NAs from the calculation. To calculate summary statistics along with standard deviation for the variable numsigmo_est, we would include these 2 commands in our program. When we run this syntax, R provides us with these univariate statistics. Looking at the output, you can see, for example, the mean, the median, and the standard deviation, along with the lowest value and the highest value, from which you could find the range. And there's also a count of how many missing values there were for this variable. It also lists the cut point for the first and third quartile of the distribution. We now know that the young adult smokers in our sample smoke on average 320 cigarettes per month. that the median of the amount smoked is 300 cigarettes per month, and that the standard deviation is about 274. So we can say that, on average, young adult smokers smoke 320 cigarettes per month, plus or minus 274 cigarettes. As you can see, that's an extremely large range in terms of cigarettes smoked and a lot of variability on this variable. But what if we add the nicotine dependence variable to the summary syntax? If we were to include the categorical variable for nicotine dependence, tab 12 MDX, in the summary syntax, R would not generate a mean, standard deviation, and other descriptive statistics, but instead would generate only the counts for each value that the categorical variable tables, here 0 and 1. So when you run the summary function on a categorical variable, you get the frequency of each level and the number of missing values. Essentially, you get the frequency distribution like you would get using the freq function. In general, it's very important to remember to use the appropriate descriptive statistics for both quantitative and categorical variables. Categorical variables can often be described well with frequency tables generated by frequency distributions and bar charts. For quantitative variables, it's best to examine histograms and then to supplement these with exact measures of shape, center, and spread.